All right, we are going to learn some things today. Symmetry within our graphs. Some of these will be functions, some of them will not be functions. But when we look at a coordinate graph, where is it symmetric? So there's two different types of symmetry. There's line symmetry and point symmetry. Line symmetry can be folded across to make two exact halves, right? Symmetric to the x and y axis. You might have done some symmetry in geometry before. So x and y axis is the line symmetry we'll be talking about, and point symmetry is going to be a rotation of 180 degrees with respect to a point. And this is actually just going to be to the origin today. So symmetric with respect to x, that's the first thing we'll talk about. That means that it can reflect across x axis. Okay, so you see that in the picture there, that there's the x-axis, and it reflects across that. It has a mirror image, right? The two halves are identical. So that's graphically how we can look at it, and this is also kind of like the description if we were to look at the points. Algebraically, what we want to do is we want to replace y with negative y. And if it comes out to be the exact same thing we started off with, then it is symmetric to the x-axis. So let's take a look at this. Test symmetry with respect to the x-axis of the relation 2x is equal to 3, Okay, so what we're going to do is we're going to replace the y with negative y. So where y is, I'm going to leave it blank, and then I'm going to put the negative y in there. So negative y squared is y, right? Y squared, 2x is equal to 3y squared minus 5. So that is exactly the same thing as our original. So yes, there is symmetry to the x-axis. Next symmetry we're going to talk about is to the y-axis. So again, this is going to reflect across the y-axis. Again, in this picture, if we see across the y-axis, those are two identical halves, right? There's a mirror image. Again, there's this little graphical way of looking at it through those ordered pairs. And then algebraically, we're going to replace x with negative x. And again, if it produces the same equivalent equation or relation from the very beginning that is given, then it is symmetric. So let's try this one. So again, I'm going to replace every x with negative x. So y is equal to x squared minus 3 times x minus 54. So you see I put the parentheses there for a reason, and then I come back and put in the negative x. So what do I get here? I get y is equal to negative x squared is x squared. Negative 3 times negative x is plus 3x, and then that minus 54 is left unchanged. Left unchanged. So is that exact? No, it is not. So it does not match the original one given. So not symmetric to the y-axis. So symmetric with respect to the origin. This means that it could be rotate around the origin. Oh, I spelled around wrong. Rotate 180 degrees, around the origin. So, if every x and y on the graph, again, this is a description of the ordered pairs. And then I have two pictures here because I'm going to show you. If I were to rotate this 180 degrees, here we go, rotate. Can I just rotate it? Nope, it won't let me. I thought this was going to be a little bit different. Let me see real fast. It's going to do that. That's 90 degrees. Let's rotate it to the right one more. So 180 degrees, does it look identical It does. So therefore, it would be symmetric with respect to the origin is what we call that. So what we do is instead of just replacing x or y, we replace both with negative x and y. So let's take a look here. We have y, so really that's negative y is equal to, in parentheses, x to the power of 3. So here we have negative x in there. So negative x cubed is negative x cubed. And then we have this negative y over here. If I divide both sides by -1, it'll be y is equal to x cubed. So in fact, it is exact, right? Exactly. So yes, it is symmetric with respect to the origin. So now we're going to do 3 examples where we're going to test all the respects. Test the respects. Is something symmetric with respect to the x-axis, with respect to the y-axis, or the origin? So we're going to start with the x-axis. I always kind of like to list it like this. I know I need to plug in a negative y. So I have x minus y squared is equal to 1. If that negative y goes in there, what is my result? X minus y squared is equal to 1. So this would be a yes. It is symmetric with respect to the x-axis. So now we'll do the y-axis. The y-axis, we plug in negative x. So I have negative x minus y squared is equal to 1. Nothing happens there. It really is different. It does change. So no, it is not symmetric with respect to the y-axis. Last but not least, we have with respect to the origin, and that means we need to replace both x and y. So we have negative x minus y squared is equal to 1. And let's put in the negative y. So our final result there is negative x minus y squared is equal to 1. And that is different from the original. So no, it is not symmetric with respect to the origin. Okay, you could pause this and do this one yourself and then check back, but I'll go ahead and do it. So we're going to start with respect to the x-axis. We need to plug in negative y. No, it is not. So this is going to be the same result because it's kind of the same thing. We're plugging in that negative x times the y is equal to 4. Negative x y is equal to 4. So no. And then lastly, the origin. Now that one might work out much nicer, right? Because we have those 2 negatives. So yes, it is symmetric only with the origin. We're actually going to find out what that means as well, if it's even or odd. All right, so 3. Algebraically show if x squared plus y squared is equal to 16. Some of you might just know what this looks like on a graph, and that's cool because we might find some good symmetry here. So x-axis, we're doing negative y. And you clearly see Same result. So yes. And then we have the y-axis. And again, you're probably going to say, well, I have to show this. I clearly can see that the y squared. I would like to see that you knew to plug in the negative y at least. You know, it's a good habit, just like I'm doing here in the notes. So, again, plugging in that negative x there. That's going to nicely come out to positive x squared. So yes, it is symmetric with respect to and if something's symmetric to the x-axis and the y-axis, it will always be symmetric to the origin. But let's go ahead and just show it algebraically. Negative x squared plus the negative y squared is equal to 16. And again, that's a nice same exact result. So yes, that is actually an equation of I would ask you out loud, it's a circle. All right. So now we're going to see if a function can be even or odd. So these are going to actually be functions. A circle was not a function. This was a rational function, actually. And this was not a function. Again, something that is symmetric to the x-axis is not usually a function. All right, functions can be even or odd. An even function has y-axis symmetry, and then odd functions have origin symmetry. So what is a cool rule here is if you test the even functions with this f of x, you can then take that result and multiply it by that negative 1, or multiply it by a negative 1, and compare it to the original. If it's equal to the original, then it has odd symmetry. Or origin symmetry and is an odd function. So we're going to graph each function. I have them graphed over here. You can graph them in your calculator if you'd like. We're going to analyze the graph to determine whether each function is even, odd, or maybe neither. And then we're going to confirm algebraically. So if something's even, it's symmetric to the y-axis. So this guy over here, if we look at it, no, it's definitely does not mirror the y-axis, right? So this is the y-axis. It does not mirror it. But if I were to rotate it 180 degrees, could it potentially be the same? The only problem I have is these mins and max, this min and max, are a little bit further away from that x-axis. So let's go ahead and test. I need to do h of negative x. So that's negative x cubed minus 0.5 times negative x squared minus 3 times negative x. So h of negative x is negative x cubed plus 0.5. Nope, not plus 0.5. I'm sorry. I was doing that too fast. Minus 0.5. Negative x squared is just positive x, so nothing would change with that. But here it becomes a positive 3x. So is this compared to the original? No, so it's definitely not even. And then if I multiply this by let me choose a different color. If I multiply this by a negative 1, I'd get x cubed plus 0.5x minus 3x. Now I look back at the original. It's not the same. This guy is different, so it's not odd. So this guy would be a neither guy. And okay. And again, you could see that on the graph a little bit too, that if we rotated it, it wouldn't exactly be symmetric to the origin. All right, let's try this one. On the graph, we can clearly see that it is symmetric to the y-axis, right? This guy right here, it definitely mirrors that. But let's go ahead and confirm algebraically. 2 over, and I need to plug in negative x. Well, in fact, negative x squared is positive x squared, and it is the same. So, in fact, it is even. If I did multiply that by a -1, no, it would not be the same as the original, obviously. So, it can't be odd. All right, let's take a look at this one. Now, this one might be odd, right? Because if I rotate it, those mins and maxes look quite high and low there. The similar distance from the x-axis. Let's go ahead and check, though. Algebraically, you put that negative in there. Negative x cubed minus 2 times negative x. This is negative x cubed plus 2x. So not even, because it is not the same as the original. But if I were to multiply that by a -1, I'd get x cubed minus 2x. And that is the same as the original, so it is an odd function. And again, odd functions are symmetric to the origin. Even functions are symmetric to the y-axis. Yeah, so I think that is it. Your homework is posted on Formative, due on Wednesday. We have a quiz on Friday that is over today's lesson, day 2 and day 1. Have a good rest of your day.